Next, we are going to look at an application example of this computation of stresses which we just saw. Okay, so let's dive in and look at a problem, and you will see that making problems on strain calculations and stress calculations using the generalized 3D Hooke's law which we just studied, it is actually quite difficult. So most of the problems in this one are essentially quite simple. So this is the problem that you have, right? So let's again, as I always encourage you to do whenever you get a problem, first understand the system first, then look at the questions, and then try to think in your head that how you are going to tackle this problem. So what you are shown over here is a thin flat member, maybe like a plate, for example. Something like this. You have a thin plate over here, right? And you have the axis which is marked, you have the x-axis and you have the y-axis going vertically up, and you have the z-axis along this particular direction, and the load is in the xz plane, right? So so suppose this is my x and this is my z, right? So your load is all on the xz plane over here, and there is practically no load on the y towards the y direction. And as you will see later in the some of the later lectures which we are going to cover, this is a classic example of a plane stress problem where the stresses are only along one plane and there is no stress along the other direction, right? So if you take a look at this problem, what it says that the thickness, the plate is made of aluminum. The thickness of the plate is 3/4 of an inch, right? So which is maybe this thickness that you have over here. So this thickness T is 3/4 of an inch, right? In within which you have a circle of diameter 9 inches, which is inscribed. So this is the circle of the diameter 9 that you have. So essentially this distance and as well as this particular distance is 9 inch, right? You're given the stresses which are acting along the sigma x. So this is the x direction, so sigma x, and to balance it out you must have the sigma x in the other side as well. So you have the sigma x along the x direction, which is a 12 ksi, kilopounds per square inch, right? And along the z direction you have the sigma z, which is 20 ksi, 20 pounds per square inch. Here also given some other information, which is the Young's modulus E and the Poisson's ratio nu, that is 1/3 or 0.33, right? So I hope the system is clear. We have a plate on which we are applying some stresses, forces along the x direction, along the z direction, no stresses along the y direction, right? And you're given information about the material of the plate in terms of the Young's modulus and the Poisson's ratio. So let's see what the problem asks us to find. The problem asks is that what is the change in the length of the diameter along AB over here. Now as you see in this figure, AB is along the x direction that we have over here. So we have to find the change in length of the diameter AB. So what the problem asks us to find is that what is going to be my delta AB, right? What is the change in the length in the diameter CD? CD is along the z direction over here, so we have to find what is my delta CD. What is the change in the thickness of the plate? So this thickness along the y direction, so I have to find what is my delta of T if the original thickness was T, right? And the change in the volume of the plate, so essentially that is delta V. So these are the four quantities that we have to find in this problem, right? Now as you can probably guess, since we are given the stresses and we are given the Young's modulus, we are first going to have to calculate the strain, and the deformations, the deltas, are directly related to the strains that we have. For example, your delta AB will be what the if your original length of AB was 9 inches, you're just trying to find the delta, right? So your epsilon x is along the x direction is going to be delta AB divided by the original length of AB, and so on. So let's dive right in this problem. So for the first one, I am trying to calculate my change in length in the diameter AB, which is along the x direction. So I am going to have to calculate what is my epsilon x. Right now we already derived, and as I said, if you write this more and more, this will sort of get ingrained in your memory. So my epsilon x is nothing but a positive of sigma x by E, right, minus nu sigma y by E minus nu sigma z by E. Correct. Now, once I have written out this particular formulation, I can easily substitute the numbers which are given to me to calculate my epsilon x, right? So here, remember, my sigma x is already given as your 12 ksi, right? Sigma y is 0, there is no force for the vertical y direction, equals to 0, and sigma z is already given, sigma z is equals to 20 ksi. Right? And also you have the value of E, the modulus of elasticity, that is given, which is the same along all the directions, direction independent. It is just depends upon the material. It is 10 into 10 raised to 6 psi. Right. So once you have these quantities, you can directly plug in the numbers within this one, and what you will get is the value of this particular parameter epsilon x. Right now, once you have epsilon x, and I'm not putting the numbers over here and computing directly, you can easily do that, or the next page I will provide the the numbers which we get over here. So once we get this epsilon x, your next step is to calculate your delta AB. Right, delta AB, remember how is the delta and the epsilons related? I know that my epsilon x is nothing but delta AB by the original length of AB. So AB over here, so that means equals to delta AB divided by my original length was 9 inch. Remember, this information was given at this particular point, 9 inch over here. So with this you can easily calculate your delta AB. So delta AB is going to be my epsilon x, which you have calculated here, right? So times the 9 inch. So you have to be careful in substituting the numbers. The in the first equation which we wrote for the strain in terms of the stresses, the KSI, the PSI, and so on. Remember, 1 KSI is 1000 PSI that you have over here. So with that you can easily calculate this one. In a very similar fashion, you can calculate your the change in length CD. Remember, CD is along the z axis over here, right? It goes along this particular z axis. So so that is going to be my epsilon z. So epsilon z will again be similar kind of an equation, sigma z by E, and is related to the other stresses using the Poisson's ratio, minus nu sigma y by E minus nu sigma z by E. Right. So once you again substitute these ones, where this one is a 0, your sigma this will be your sigma x, not sigma z. You are given your sigma x as 12, sigma z as 20 k size, right? You can calculate this one, and this will again, once you calculate these quantities, this will again help you get your what is your delta CD. Right. The last bit is that you have to, or the second last bit is to calculate the thickness of the plate. So remember, the thickness can be, this thickness can be easily expressed. This thickness is about this y direction over here. So I have to find my epsilon y, right? So epsilon y is in this case is again going to be sigma y divided by E minus your nu sigma x divided by E minus nu sigma z divided by E, where here I have no stress about this y direction over here. So this is 0, and the others you have 12 and 20. So with that you can calculate this one over here, and with that you can calculate your delta of your thickness T, right? The original thickness, remember, is given as 3/4 of an inch over here, so you can calculate that. Right? So that solves your this one. The last one is to compute the volume of the plate, and you can do it in two ways, equivalent ways. The first way, what you can do it, remember the original volume is what the original volume is simply your 15 times 15 times this particular thickness over here. So that is your original volume, and now after that you have calculated your delta AB, delta CD, and delta T. So you have calculated the changes in length, so you can calculate the final volume, and you can do the final volume minus the initial volume to get the change in volume. The other way to do that, essentially equivalent way, that remember that we had looked at the concept of dilation, the term E which we looked at. The E was simply your sigma x plus sigma y plus sigma z, right, for that unit cube which we had looked at. And what was the what was E was an expression of your change in volume divided by the original volume of a unit cube, right? So E is nothing but delta V by V, right? So with this one also you can simply calculate that what is your delta V, because remember the change in volume is simply the delta V. It is going to be E, which you calculate from this particular equation times the original volume, where the original volume, as we just figured out, it is going to be 15 times 15. So the length into the width times the height times t, right? So you can simply substitute these numbers and you can calculate all of these questions which are over here, right? So in the next page I have given the solution for this particular problem. So as I said that your epsilon x, you calculate the epsilon x's, you substitute the numbers carefully. You have to be careful of the units that you're calculating, right? Now you calculate your epsilon y and epsilon z in a similar fashion. Now once you have these epsilon x's, this is the relationship between your the change in length to the original length, which is your each of these epsilons. So to find the change in length, you multiply the epsilon with the original length, the d, which is the diameter for this AB and the CD, these inscribed circles that you have over here, right? And the last one is this delta t, which is the change in thickness. So that's how you calculate these numbers. Please compute on your own, and if you see get the same numbers or not, and while you're computing you will see that whether you are messing up with the units anywhere. So that gives you this box that you see over here. And then you have the change in volume. You can simply calculate the final volume after you have the change in the length, and then you subtract the original volume 15 times 15 times the t, or you can simply calculate the dilation E over here, and you calculate the change in volume as simply as a product of E times the original volume. So I hope this problem was clear to you. Solve similar problems on your 3D Hooke's law, where you have different loading conditions on different kinds of structures to find the stresses and the strains and so on.